Hello, class. My name is Guy Wilson, and I'm here to show you my presentation on diagonalization. So, to kind of get started, a good question is, what is diagonalization? And it's um, part of a few things that, just to get into it, you want to know how to do and understand matrices, vectors, linear transformations, the inverse of matrices, and their determinants. And given a linear transformation of the type T of x equals ax, A is diagonalizable if there exists a matrix B of T with respect to some basis that is diagonal. Or in other words, matrix A is diagonalizable if we can find a matrix S and the diagonal matrix B such that S inverse AS equals B. So why not go ahead and try out an example of showing a diagonalizable matrix? So given the following linear transformation, let's show that it's diagonalizable. And the first thing we want to do is find the eigenvalues. And we get that from the characteristic polynomial, which we will find using this equation. The determinant of the matrix, we'll call it A, minus lambda times the identity matrix. And since the identity matrix is a diagonal matrix, that will give us 2 minus lambda, -3, 1, -2 minus lambda. And we're still looking for the determinant. And looking and seeing that we have a difference of squares there, we can see that the first diagonal multiplication will give us lambda squared minus 4. And then we're subtracting -3, so +3, which will give us lambda squared minus 1. And notice that that's also a difference of squares, which is lambda minus 1 times lambda plus 1. And now if we imagine there's also a little 1 at the top of these, we can see that the multiplicity, we call that the multiplicity of the eigenvalue, which is 1 for each eigenvalue. Showing us that we have two eigenvalues, lambda equals 1 and lambda equals 2. Sorry, lambda equals -1. So now we have our eigenvalues, and we want to calculate the eigenvectors for each eigenvalue. So starting with lambda equals 1, we want to have and show the eigenvectors by doing the calculation A minus lambda I times lambda times the identity matrix times x equals 0. So we solve this by taking our reduced row echelon form. And in this case, with lambda equals 1, 2 minus 1 is 1. And this is just -3. That's just 1. -2 minus -1 is -3. And finding our reduced row echelon form, we just subtract the first row from the second, and that leaves us with 1, -3, 0, 0. And that takes us to our solution, which shows us that x1 equals 3x2, and that solution yields x2 times the vector 3, 1. And then we do it again for lambda equals -1. So writing out this matrix, same thing. A minus lambda times the identity matrix gives us 2. 2 minus -1 is 3. And that stays -3. That stays 1. -2 minus -2 minus -1 is -1. And doing the reduced row echelon form gives us, um, well, we'll just convert the first row to 1, -1, and then that will give us Subtracting the first from the second will give us 1, -1 at the top, and 0, 0. And in this case, we can see that x1 equals x2, and that gives us the vector 1, 1. And these are the eigenspaces for each one of our eigenvalues. One thing to kind of note about the multiplicity here at the top is that there's two eigenvalues of multiplicity 1, and those add up to 2, which is the same dimension as our matrix. Um, Now, with our eigenvalues that we have here, when we put them together, we get our eigenbasis, and we'll just call that our S, which is 3, 1, 1, 1. And that is how we just shown our matrix is diagonalizable. And just to kind of, if we wanted to mathematically, prove that the equations presented in the last slide hold true, just for the sake of time, I've already calculated the inverse of S, which is 1/2, 3/2 along the diagonal, and then -1/2 and -1/2 here. So if we wanted to do um, S inverse A, that equals, I have already calculated this too. 1/2. Don't worry, I can't do this in my head that quickly. -1/2, 1/2, -3/2. And then when we add on the additional S, that comes out to be 1, -1 during the diagonals, and then 0, 0. And 1, -1, notice that's the same thing as our eigenvalues. And that's just more verification that we did it right. Hooray! Awesome. So for the next one, we have, this is just moving on to another example. We show that this one's diagonalizable by, again, calculating the determinant. And that comes out to be the determinant of, like we said before, we just put our lambdas in our subtracting piece, and the rest stays the same. That comes out to be actually just lambda squared, where we have lambda equals 0 as our solution, which leaves us with a multiplicity of 0. And since our multiplicity is 0, um, it needs to be at least 2 to actually be able to be diagonalizable. So in this case, it's not diagonalizable. The multiplicity is too low. And yeah, that's kind of one of the easier ones to go through. Um, so to kind of fully sum everything up, the steps that we want to go through are, we find our characteristic polynomial, and from there we use that characteristic polynomial to get our eigenvalues, and then for each one of those eigenvalues we find an eigenvector, and these eigenvectors together make up an eigenspace for each eigenvalue, and then we combine these eigenspaces to create an eigenbasis, and that's how we show that we have our diagonalizable matrix. So thank you all for watching. I wish you all well and a safe and happy holidays. Bye.